Hello, in this video, we'll see how to derive the expression for phase voltage in terms of symmetrical components. But first, let us understand what symmetrical components are. Electrical power systems normally operate under completely balanced conditions. In such cases, the system impedances are identical and the three-phase currents and voltages are balanced. The knowledge of voltage and current in single phase is enough to completely analyze the system. However, external factors like lightning or a tree branch falling on the system can cause faults such as three-phase faults or line-to-ground faults. This causes a balanced system to become unbalanced. To analyze these unbalanced conditions, we use symmetrical components. Symmetrical component analysis can transform an unbalanced condition into symmetrical components. It computes the system response by straightforward circuit analysis on simple circuit models and then transforms the result back into their original phase variables. In symmetrical component analysis, unbalanced three-phase voltages and currents are transformed into three sets of balanced voltages and currents. These are the positive, negative, and the zero sequence. The first figure shows a balanced system. Here, the voltages are in phase and lag each other by exactly 120 degrees. However, in an unbalanced system, we see that the voltages are not at 120 degrees to each other. This is an unsymmetrical system. Consider the symmetrical system of phasors as shown in the figure. Being balanced, the phasors have equal amplitudes and are displaced 120 degrees relative to each other. By the definition of symmetrical components, the vector VB1 always lags the vector VA1 by a fixed angle of 120 degrees and always has the same magnitude as the vector VA1. Similarly, the vector VC1 leads the vector VA1 by 120 degrees. Having known that, we can say that the vector VB1 will have a magnitude of 1 and be at an angle of 240 degrees from VA1. The vector VC1 will have the magnitude of 1 and be at an angle of 120 degrees with respect to VA1. Hence, we can deduce the formulae that the vector VA1 will be equal to VA1. The vector VB2 will be equal to A square VA1. The vector VC1 will be equal to A VA1. In the previous formulae, the subscript 1 designates the positive sequence component. The system of phasors is called positive sequence because the order of the sequence of their maxima occurs in the form ABC.
Similarly, in the negative and zero sequence components, we deduce VA2 is equal to VA2, vector VB2 is equal to A VA2, vector VC2 is equal to A square VA2, VA0 is equal to VA0, VB0 is equal to VA0, and VC0 is equal to VA0, where the subscript 2 designates the negative sequence component and subscript 0 designates the zero sequence components. For the negative sequence phasors, the order of the sequence of the maxima is CBA, which is opposite to that of the positive sequence. The maxima of the instantaneous values for zero sequence occurs simultaneously. Figure 1 shows the positive sequence ABC in which B lags A by 120 degree and C lags B by 120 degree. The second figure is a negative sequence ABC in which C lags A by 120 degree and B lags C by 120 degree. The third figure is a zero sequence in which the vectors A, B and C are in phase.
In all three systems of the symmetrical components, the subscripts denote the components in the different phases. The total voltage of any phase is then equal to the sum of the corresponding components of the different sequences in that phase.
It is now possible to write our symmetrical components in terms of three, namely those referred to the A phase, that is VA equal to VA0 plus VA1 plus VA2, and VB equal to VB0 plus VB1 plus VB2, and VC equal to VC0 plus VC1 plus VC2. We may further simplify the notations as follows. Define V0 equal to VA0 and V1 equal to VA1 and V2 equal to VA2. Substituting their equivalent values, we get VA equal to V0 plus V1 plus V2 and VB equal to V0 plus A square V1 plus A V2 and VC equal to V0 plus A V1 plus A square V2. These equations may be manipulated to solve for V0, V1 and V2 in terms of VA, VB and VC. Then we get V0 equal to 1 by 3 of VA plus VB plus VC and V1 equal to 1 by 3 of VA plus AVB plus A square VC and V2 equal to 1 by 3 of VA plus A square VB plus AVC. It follows then that the phase currents are IA equal to I0 plus I1 plus I2 and IB equal to I0 plus A square I1 plus AI2 and IC equal to I0 plus AI1 plus A square I2. The sequence currents are given by I0 equal to 1 by 3 of IA plus IB plus IC and I1 equal to 1 by 3 of IA plus AIB plus A square IC and I2 equal to 1 by 3 of IA plus A square IB plus AIC. The unbalanced system is therefore defined in terms of three balanced systems. Equation 7.6 may be used to convert phase voltages or currents to symmetrical component voltages or currents and vice versa as shown in equation 7.7. The slides 1, 2 and 3 are explained by Harshita and the slides 4, 5 and 6 are explained by Purna Mujumdar and the slides 7, 8 and 9 are explained by Sumit Verma and the slides 10, 11 and 12 are explained by Nikita B. Thank you.